cybernetics or some ideas from the cybernetic past can help us to bring together two broad wings of contemporary cognitive science. So what we might call the computational tradition, the kind of mainstream computational tradition in cognitive science, and some of the anti-computationalist embodied or inactive traditions. Can everyone see my slides okay there?
Yeah.
Yeah, perfect. And so I'm calling this computers with bodies. So the idea here is that a positive route forward for contemporary cognitive science, which I think is stuck in some ways, would be to emphasize these two distinct aspects, so that cognitive systems are computational systems on the one hand, but that they're also embodied systems, and we need to take into account both of these aspects when we're studying them. And here it is that I think cybernetics has got a really rich history, and we can trace both of these kind of distinct research projects back to the history of cybernetics. So the first part of this talk will be somewhat historical. So I'll talk about these two twin origins in cybernetics, and this should be somewhat familiar to most of you. So my apologies if that bores you somewhat, but hopefully my spin on it will be somewhat different. And then I'll talk about what I mean by computers with bodies and what these two different research traditions are, computationalist and anti-computationalist, and how we might be able to bring them back together by drawing on some cybernetic resources, and then sketch out what this might look like. Okay. So like I said, I think the cybernetic origins of cognitive science and contemporary cognitive science are somewhat forgotten and understudied. These are two notable exceptions, but in most histories of cognitive science, you probably won't even find the word cybernetics anywhere. It's just not mentioned. To some, well, nowadays I think this is because people just don't really know about cybernetics, or they think it's something weird to do with management studies or architecture or some other discipline that it's now grown into. Maybe in the 80s and 90s, there was a particular strand of cognitive scientists who were somewhat embarrassed by their cybernetic history. I'm sad to say, as seeing it as this kind of strange oddity. But I don't think we need to do that, and I think it's much more positive to actually think about it. So here I've just got Margaret Bowden's 2-volume Mind as a Machine History of Cognitive Science, which doesn't say so much about cybernetics, but she does have one section, one chapter which talks about it in some detail. On the other hand, we've got Jean-Pierre Dupuis on the origins of cognitive science, all about cybernetics, and I think a really fascinating book, which I would highly recommend if you are interested in these connections between cognitive science and cybernetics. Dupuis' perspective on a bit of a tangent here is particularly interesting, I think, because he's actually very skeptical of the contemporary computational cognitive science project. So he brings this kind of outsider perspective on it, and some insights into why this might be a kind of misleading approach, but very interesting book. I would highly recommend. So what are these origins? There are two strands of this, as I said, one to do with the computational tradition and one to do with the embodied tradition. And I'll go through each of these in turn and say a little about them. Okay. So, this is just, sorry, some more history of just to give an overview for anyone who might be in the audience under my invitation and doesn't know so much about cybernetics. The cybernetics movement as such, I would say, emerged out of interdisciplinary research in the US during World War II and other places. So people from lots of different disciplines working together. In particular, people interested in problems of control, so how to control weapon systems in particular during the war, but also other kinds of problems. This led to the Macy conferences between 1946 and 1953, which were eventually termed the cybernetics conferences, and brought together these people with lots of different background interests. So a few figures here we can see, if I get my little laser pointer up. It's quite bad quality picture. I'm sure there's a better one somewhere. Warren McCulloch here, I believe Margaret Mead here. The others I can't make out so well, but a bunch of people. Von Neumann attended some of these conferences, among others. These, I suppose, fragmented by the mid 50s. People started going their own separate ways. But during this half decade, there was a lot of very vibrant ideas being discussed and passed around, and this led to lots of interesting research in different areas. The term cybernetics, I won't talk about so much here, was coined by Wiener, of course, in 1943 as the science of communication and control, something which I think is still very central to cognitive science today. so by the mid-50s, the cybernetics movement as such had begun to splinter and head in different directions. In 1956, we have another famous conference or workshop, the Dartmouth workshop, where the discipline known as AI or artificial intelligence was first kind of started, where it all came together. And I think, notably, there was some feedback there, good cybernetic theme. Notably, very few participants from cybernetics conferences only 3 years earlier attended the Dartmouth workshop. So quite a different group of people, maybe with some different aims in mind, and not much discussion of the same ideas from cybernetics. And so Claude Shannon here would be a notable exception, I think. I'm not sure any of the other main attendees of the Dartmouth workshop on artificial intelligence were involved in the cybernetics conferences. This approach, this very kind of computational heavy approach of the Dartmouth workshop is probably one of the birthplaces of cognitive science, which then develops over the next few decades into a kind of coherent research program. Sometimes, again, so an interdisciplinary research program like cybernetics. Sometimes linking together these 6 disciplines is a common way of framing it. So psychology, philosophy, linguistics, anthropology, neuroscience, and artificial intelligence. So yeah, again, like cybernetics, big interdisciplinary program. Not much mention of the cybernetic history, though, in any of these disciplines, I would say, today. Anthropology is maybe a little bit of a kind of redhead stepchild here, who doesn't have so much to do with cognitive science for a lot of this period. And maybe where you would find some more cybernetic currents within cognitive science if it had been more closely involved. So people like Margaret Mead were very important in 20th century anthropology and had a strong interest in cybernetics. Gregory Bateson as well. So that may have could have been another way of getting cybernetics back into cognitive science. But I think by the 90s and certainly today, there isn't much knowledge or awareness of the cybernetic past of cognitive science, and this is something I'd like to try and change a bit. Okay, so the first of these connections here, computation, and 3 or 4 big figures here who were all at least somewhat associated with cybernetics, maybe some more famously than others. Alan Turing, John von Neumann, and Warren McCulloch and Walter Pitts. Walter Pitts over here. And I'll say a little bit about each of these. These figures are all more well known, I would say, in contemporary cognitive science, but their connections with cybernetics are less well known. And it's interesting to look back at this and look at the kind of influence they've had on cognitive science, in particular the idea of computation. So Alan Turing probably needs no introduction. Famous British scientist of the 20th century. In 1936, wrote this paper on the halting problem, where he posed the idea of the hypothetical idea of a Turing machine as a kind of abstract logical system which could carry out any computable function. It ends up being a somewhat circular definition because a computable function is just defined as a function computable by a Turing machine, but it's still a very interesting idea and has been incredibly important in lots of different areas of mathematics and computer science. Indeed, there wouldn't be computer science as we know it without this paper. This is a kind of schematized diagram of a Turing machine. So it's just an extremely simple device with a what's called a head or a kind of a box which reads a tape of what are essentially ones and zeros, so marks and blank spaces, and either writes a mark, deletes a mark, or moves the tape one way or the other. And just this extremely simple kind of system with some set of instructions can carry out what we would now think of as any computable function. So he, I think, here provided a very vivid illustration of the idea that we could mechanize what are previously thought of as intelligent operations. So logical or mathematical operations could be mechanized and performed in a kind of unintelligent manner. And this proved extremely important for what would become cognitive science, and particularly the computational tradition. because you then get the quite natural next thought that thinking as a kind of logical operation could be mechanized in this way, and thinking could therefore be understood as computational. And then if we can understand what kind of computation it is and how it's implemented, we'll be able to understand what thinking is. And then, if you're interested in the engineering side of this, you could make a thinking machine yourself. You could create an artificial intelligence. Turing's connection to cybernetics is probably less well known. He was a member of, or gave one talk for the Ratio Club, the kind of British cybernetics club during the 40s and 50s. We were talking about Craig earlier, and the president of the Ratio Club, I think, described it as a club for those who were doing cybernetics before Wiener invented the term cybernetics. So there's a kind of slight British chip on our shoulder feel here that we were doing it first. We just didn't come up with the fancy name like the fancy Yanks did. But yeah, Turing was in the same circles as lots of the members of this club, who we'll come to later. Exchanged some interesting letters with Ross Ashby in particular, and gave at least one talk to the club. So not closely associated with it, but I think closely associated enough that we should think of him as a cyberneticist, or at least as much as many of these other figures. Some of his later work you might think of as moving in a kind of cybernetics type direction, or something I think is connected to that. So he has this very interesting later work on pattern formation, which begins to look at complex systems and the emergence of patterns out of very simple structures and this kind of thing, which I think is another kind of useful theme. So Turing, I think of as a cyberneticist, and in many ways the founder of computational cognitive science. A very different character, John von Neumann, in the US, attended several of the Macy conferences, so in that sense is associated with cybernetics, and among the many different things he was involved in, created the idea of what is now known as a von Neumann architecture, which is the kind of at least kind of architectural structure in now a more abstract sense, but originally a more literal sense of your desktop computer, and also went on to inform a lot of computational cognitive science. So this is a von Neumann architecture. So the idea is, rather than just the Turing machine, which only has this single tape to run along, you can structure things such that you have a control unit similar to the head of a Turing machine. These kind of logic units, which just do basic functions, so core functions, and then a memory unit where you can draw up what are essentially different Turing tapes for different kinds of problems you need to solve. And this moves the kind of abstract idea of a Turing machine, which is in some sense not physically plausible, because it would take either or both too much room and too much time to compute these functions, into something which we can actually use and actually build. So you can see the shift to the von Neumann architecture as a way to make the idea of a universal computation from Turing into something real, something concrete. So the idea here is you give some input to this. The control unit works out what kind of input it is and what we want to do with it, and then gets up whatever instructions we need from a memory unit, and then uses the other functions to perform the computation, and then stores something back into memory and gives us some kind of output. This could be an output for us to read in text, or an output that controls some other system. So we don't need to just think of the computers we use, but you might think of a computer attached to a actuator such that it can actually do something in the world. And this again gets us closer to the idea of either artificial intelligence systems using this kind of architecture, or the idea that the human and other cognitive systems might also have this structure. And lots of classic work in computational cognitive science, I think we can see, is taking this general framework and trying to find where these bits are in the human brain. So if we think of a brain as a computer, we try to work out where the memory bits are, where the central processor is. People think maybe the frontal lobe kind of has this structure, where the different functions are carried out. This is maybe seen as a somewhat misguided approach, I would say, by some people today, who instead would look for what we would call an abstract machine in computer science, or a virtual machine. So rather than thinking there has to be a single place in the brain where there's a control unit, we might think of it as a kind of distributed network. But this idea that we want to kind of localize different specific functions corresponding in some way to computational functions is still very much present in contemporary cognitive science. So this would be another cybernetic forerunner of cognitive science. This might not look much like a cybernetic system to some people, but I think we still got this idea of it being used to control things. And one thing I'll get to later is if you imagine a loop between output and input, we get something much more like a feedback system. So if a computational system like this is taking kind of sensory input from its environment and also changing things in that environment, which it can also interact with and see, you get something much more like a feedback loop. And this I would like to suggest later on is how we should think about human computational cognition in a more kind of cybernetically informed fashion. Finally, we've got Warren McCulloch, very involved in the Macy conferences, and Walter Pitts, who was his kind of brilliant protege, quite a tragic life, if you're interested, look into that. But they published this paper on what's come to be known as the logical neuron, or the Warren McCulloch neuron. And this was looking at the physiological properties of neurons in the brain in quite an abstract sense, and modeling how they could work as very basic logic units. So roughly how a neuron works, or how they were modeling a neuron as working, is it takes a bunch of different kinds of inputs, so excitatory or inhibitory inputs, which raise a kind of electronic threshold in the neuron. And once this passes a certain threshold, the neuron fires, which means it sends an input or a signal to some other neuron. And even though this is modeled often as a kind of an analog system where you've got a gradual raising of the threshold, these still have the same abstract properties as binary or digital logic gates. So if you have a system which fires if it only gets one input from one direction, this can be performing something similar to an OR. Or if you have an input neuron which needs inputs from two directions, that might look like an and so on. So you can use these kind of analog or biological neurons, at least in principle, to build something at least formally equivalent to a digital computational system. So what you get from McCulloch and Pitts, I think, is at least the sketch of an idea of how to think about biologically plausible neurons as computational systems, and that's still very much a live research program in cognitive neuroscience. So well, there's two parts to that. The people who think the brain is a computer really need something like this to be true, or else you're not going to have a plausible story about the implementation. But then on the other hand, you have people studying individual neurons and working out what their computational properties are like. And it turns out that they're much, much messier than the systems we use in a computer. So there's still a long way to go on that. But I think the idea that you can treat a kind of messy biological system as having some kind of abstract computational properties is a very valuable one that you get coming out here. Okay, so that's the computational part of the tradition there. Yeah, thanks James. A link to a very interesting, that's Phil Husband's History of the Ratio Club, which is a very good one. Very interesting bunch of people. They had one talk about telepathy, which is notable, but that was very much a live idea back in the 50s as well. Okay, so I'll say a little bit about embodiment, and here we actually get back to some of the British cyberneticists who, I think, in contrast to the American cyberneticists, so von Neumann and Claude Shannon and Norbert Wiener were maybe more interested in the embodied and kind of engineering side of things. So I'll say a little here about Ross Ashby, Gray Walter, and not a British figure, Heinz von Förster here, who was important in what became known as second-order cybernetics, which I think has had a more direct influence on some of the anti-computationalist cognitive science today. Cool. So Ashby's homeostat, again, something I'm sure a lot of you are familiar with. This was just a kind of mechanical implementation of a homeostatic system. But so the idea, you have here pools of water inside here with current running through them, and you can set the dials to different levels, to different kinds of settings. And what he found interesting about it is you'll reach a kind of equilibrium where these reach some kind of steady state. And he explicitly intended this as a kind of very simple model of something like a cognitive system. So it seems to find its way towards this steady state. And this was how he thought about cognition. and how he thought about other kinds of behavior like that. There's an interesting exchange I mentioned earlier between him and Turing, where Turing says, Ashby, this is all well and good, but why don't you just simulate this on my big computer I've been building up in Manchester? And Ashby seems, I think, a bit exasperated, because I think to him this really misses the point. If you're just simulating something, you're not really understanding it. You need the actual physical body of it to understand it. I won't say much more about Ashby, but I think this idea of homeostasis is extremely important here. And another bit of Ashby's thought, the good regulator theorem, has informed some later work as well by some of the cybernetics, some of the modern people here today. How am I doing for time, John? I'm not quite sure when we started. Sorry, you're muted there. Yeah.
8 minutes.
Okay, cool. I've run a little bit late there. Okay. I'll skip through some of this and get to what I actually want to talk about. Sorry, the history one on a bit. Walter's tortoises here. Just again, this is a kind of embodied robotic system. I did have a video to show you, but I'll send a link to it because I just really love this video. I think it's fantastic. And I won't show it to you though because we don't really have time. It's just a video. It's an old BBC video about Walter's tortoises, which I would recommend you all watch if you haven't seen it. Then we get to von Förster and second order cybernetics. And all I want to say about this is that it informs what becomes known as the enactivist tradition in cognitive science through the autopoietic theory of Maturana and Varela. So Maturana and Varela were Chilean cognitive scientists, or perhaps cyberneticists, who developed what was known as autopoietic theory, which envisioned a cognitive system as a kind of functionally closed system, which just reacted to perturbations from the environment. And what's important for the anti-computationalist tradition here is that this was seen not as a system which would represent its environment, but instead had its own kind of meaning wrapped up in its own homeostatic system here. Okay, so what I wanted to say about this is just that contemporary cognitive science, as I've mentioned a few times, has this emphasis on computationalism. So the idea here that we come up with a computational theory of how the mind works. We work out what this might be in algorithmic terms, and we work out how to implement it in the brain, for instance. There's another tradition inspired by both second order cybernetics and Maturana and Varela's autopoietic theory, the embodied tradition, or the inactive tradition, which denies that this computational approach will work. And they deny that the computational approach works because it sees the mind then as a kind of passive receiver of inputs. So not an active agent in its environment, just this passive thing. So they emphasize these kind of interactive loops between the environment. So they see cognition not just as a passive process of computation, but rather an active process of interaction with the world. And in particular, one thing they dislike a lot about computation and computational theories is the emphasis that they think, at least in the 90s, computational theories put on representation. So the idea that thinking is a process of representing things in the world. And I think to them, this introduces a kind of a split from the world. So there's this kind of epistemic boundary where we're closed off from the world and we're kind of stuck in our own little cinema representing it. And that's how they characterize computational theories of mind, as opposed to these embodied or inactive theories, which don't have that kind of boundary. Instead, we're in direct connection with the world. And the connection with cybernetics again here is that, you know, this is very easily seen as a kind of feedback loop, and this idea that there's this constant process of balancing our interaction with the world going on there. The main thing I really want to emphasize here is that there are these two strands present in contemporary cognitive science, so the computational and the embodied, or the anti-computational. But I think it's really a mistake to see these as being in opposition, and the mistake comes from this thought that computation has to be representational. So computational has to be a matter of kind of building a picture of the world and then processing internally on it. So yeah, that's just a picture of some kind of schematic picture of a computation. So I've written a bit about this, but won't talk about it so much today. There's a lot of contemporary research in philosophy of computation arguing that we don't need to think of computation in this representational way. So instead, we can think of computation as just the manipulation of these units, these digits or whatever, which don't have any inherent meaning. So the computation itself doesn't need to be seen as meaningful or as representational. And I think this means it doesn't need to introduce this division between us and the world. Instead, it can just be what's called a mechanistic explanation of what's going on internal to a system. And that mechanistic explanation, I think, isn't going to be the full picture of what cognition is or how cognition operates. Instead, it just gives us one half of the picture, the kind of internal bit, whereas the external bit might be something else. I'll skip that and this. That's just a nice artificial life picture. The only reason I included that, I won't say much about it, is just that I think it gives a very vivid illustration of how something complex and emergent and creative can come from very simple computational rules. So this is just each of these cells just either dies or expands depending on these very simple rules, and yet we can get something looking like life from it. So I think this idea that computation and life or cognition might be separate is a mistake there. Okay, in the final few minutes, I'll just say a bit about some contemporary traditions in cognitive science, which I think draw on the cybernetic past in a more interesting way, and I think are valuable to look at. This is Rodney Brooks, Anil Seth, and Cal Friston. Rodney Brooks now, so in the 90s, he was doing this work on embodied robotics, and he's still pursuing this in a private enterprise now. iRobot, I think his company was called last. And he had this very interesting idea of a subsumption architecture, which is a computational or robotic system, but rather than explicitly representing rules about the world, just follows these very basic sets of instructions. So, unless it's told to do something else, it will wander around. But then, when it gets a sonar signal of something in its environment, it will try to avoid it. And you get a much more emergent behavior here, not based on any explicit rules, but rather just these different kinds of interactions of internal parts of the system. And I think his robots, I think, are somewhat inspired and very reminiscent of Gray Walter's robots, like Elsie and what the other one was called, and have this kind of emergent quality to them. And I think this way of thinking about computation and robotics is quite an interesting one when we're thinking about what kind of natural cognition might be like, and is going to be much more fruitful than the kind of strict rules-based approaches of more classical artificial intelligence. Some of the contemporary robots, like that we see Boston Dynamics doing, the big dog and so on, I think they have more explicit rules-based systems, but they're also using features of their embodiment in a useful way. So, for instance, by having slightly non-rigid limbs, you can save a lot of computational power because you don't need to work out exactly where the limb should be because there's some give in it. So this idea that some aspect of internal computation can be offloaded onto the body as well is something coming back into some of contemporary cognitive science. So both Anil Seth...
You need to be winding up fairly shortly, Joe.
Cool. So just to end then, just so that I won't say anything about this, Anil Seth and Carl Friston then are both working within this active inference framework, which is draws some explicit inspirations from cybernetics, and again emphasizes ideas like homeostasis and interaction with the world. So seeing cognition not as a matter of passively receiving input and computing over it, but rather trying to come into some kind of equilibrium or balance with the world, closer to the idea of a cybernetic system. Yeah, finally, just to sum up this, so I think we have these two different traditions which, with a kind of cybernetic vision, could come back together. So on the one hand, computation or mechanistic approaches, which excel at explaining the internal structure and workings of complex systems, like the brain or like cognition, and embodied and active approaches, which excel at explaining the interactions between a system and the world, and maybe even how meaning can arise from those interactions. So Vina's early paper here on the feedback loop as a kind of source of meaning, I think, is interesting in this regard. And I think looking back to the cybernetic tradition for contemporary cognitive scientists can help us synthesize these two kinds of rival approaches. So I'll just sum it there. That's a paper about from some ardent computationalists pushing this kind of line as well. I think that we can bring these things back together. Cool. So I'll sum it there. Thanks very much.